Hi, and welcome back to today's session where we will finally see how to actually quantify aleatoric and epistemic uncertainty in Bayesian neural networks. Bear with me with today's session because there will be a little bit of math, but again, I try to make it as easy to follow as possible. And I guess it's still nice to actually see how it works in practice, because then in the end, if you actually use those methods, you will know what happens there exactly. Okay, so today we're going to look at just my laser pointer, here it is. We want to quantify total uncertainty and the parts that are aleatoric and the parts that are epistemic. And how it looks like, I mean, the math looks a little bit complicated, but just remember this H or eta, the Greek letter eta, here is just the mathematical formula for the entropy. This E here is the expected value given all the weights of our posterior of our predictions given the data and the weights, which kind of makes sense because the entropy just measures the uncertainty or the chaos of the predictions, and the more spread out the expectation over the predictions is, the more uncertainty or entropy we have. The aleatoric part is the expectation over the entropies. So here the difference is the total uncertainty is the entropy of the expected prediction versus the expectation over the entropies. Because we consider multiple models, and we can first calculate the entropy and then calculate the average or the expected value over the entropies, or do it the other way around. And then the remaining part is the epistemic uncertainty, and that's also how it's usually calculated. So you basically calculate the total entropy minus the aleatoric part, and this gives you the epistemic uncertainty. And this is exactly what's described with this letter I here, which stands for the mutual information between the prediction and the model parameters. And the definition of it is literally just the entropy of the expectation minus the expectation of the entropies. Okay, so this again looks maybe very abstract, so let's look at specific numbers. Imagine here we have two models, P1 and P2. So those are two neural networks that we sampled with two different sets of weights, and we want to predict one example X. So this could be, for example, one image, one text, one new observation in your tabular data set, whatever. And the output of the neural network with the one configuration is this, that it gives 99% of probability mass to class 1 and only 1% to class 2. However, our second neural network, our second output, predicts exactly the other class with a probability of 99%, and here class 1 only has the probability of 1%. So without looking on the math first, I want you to maybe just pause the video for a second and think about what kind of uncertainty does this setting represent? Is this high aleatoric uncertainty or high epistemic uncertainty? Okay, so this is a very classical example of high epistemic uncertainty, because the two models, they just do not know which class is the right one, but they are very certain that it's either the one of them. So this relates to a lot of epistemic uncertainty. And now let's look if the math tells us the same. First, we want to know the mean predictive distribution, because if we remember, we want to know the entropy of the expected, so the entropy of the mean. For this, we need to calculate the mean. And basically, since we only have 2 examples, we calculate both together and average them. And since they both add up to 1 here, we have a mean predictive distribution of 0.5 and 0.5. Which means our total predictive uncertainty, the entropy over this mean distribution is, and this is just the formula for the entropy, so minus times the probability of the times log probability of the first class plus probability times log of probability of the second class. And now if you just plug that into your calculator, we get a value of 0.6931. Okay, so now we know the total predictive uncertainty. Now I will remove this image and calculate the aleatoric and the epistemic part. The aleatoric part is the mean over the individual entropies. So here you can again see how it looks like and that it actually matters whether you calculate the entropy first or calculate the average over the predictions or the expected value first. Okay, so the average over the individual entropies, and we have model 1 which has 0.99 and 0.01. And the second model is exactly the other way around. So the 2 entropies will be the same, since entropy is a symmetric function. For us, for the entropy, it doesn't matter which class is class 1 and which one is 2. You can also just switch them around and the entropy will be the same. So 1/2 times 2 times the same entropy cancels out. So we will just calculate the entropy for one of those models. And again, it's probability times log probability for all the classes. So this is for the first class, plus probability times log probability for the second class. Don't forget your minus sign in the front, and we will get a total aleatoric uncertainty of 0.05. Now the epistemic part is total minus aleatoric, this number minus that number. So we can see that we get an epistemic uncertainty of 0.63. And if you compare the total and the epistemic one, you can already see that basically most of the uncertainty here comes from the epistemic uncertainty. Or if we look again in a graphic, it looks like that. This is just how the class distributions are for the 2 different models. And the total uncertainty is 0.69. The epistemic part is 0.63. Okay. Now let's look at the second example, but without going through the whole math again. What happens if both models are uncertain? Now I want you to, again, pause the video for a second and say what kind of uncertainty is represented here. Okay, I hope all of you guessed that this is aleatoric uncertainty, because we just don't know which one is the right class. So the first model predicts 50% and 50%, and the second model predicts 51 and 49. So they don't predict exactly the same, so there is a little bit of epistemic uncertainty left. But they are both very uncertain which class is the right one. So this really represents this inherent randomness where we just cannot tell which class is the right one. And now if we again look at the total uncertainty, we see that we have a total uncertainty of 0.69. So this is the total uncertainty is quite similar in both of the cases. And the epistemic is 0.00005. So it is very, very little, and most of the uncertainty comes from the aleatoric part here. Okay, so now we looked at the 2 extremes. We had one where we had a lot of epistemic uncertainty. We had one example where we had a lot of aleatoric uncertainty. And now I want to show you a third example where the total uncertainty differs a little. Namely here, example 3, where we have model 1 that predicts class 1 with 75% probability and 0.25 for the second class, and a second model where it predicts 0.8, so 80% for the first class and 20% for the second class. So in this example, the total uncertainty is less than before. It's because the models still agree which class is the right one. So they both have more probability on the same class, namely the first one. And again, there is a lot of aleatoric uncertainty happening here, because we are not like 99% sure that class 1 is happening, but we only have like 3/4 and 1/4, or here 80% and 20%. Okay, thanks for bearing with me with this math session. I hope you still found it interesting to see that even though those concepts are quite abstract, we can get to real numbers and real uncertainty quantification values by just calculating entropies. We are funded by the Deutsche Forschungsgemeinschaft and copyright. Thank you.